Welcome back. My name is Ariel Rokem. I'm one of the core developers of DIPY, and in this talk I'm presenting a few of the tools that we've built on top of DIPY in order to do automated fiber quantification, visualization, and insight. In this last video, I'll talk about machine learning tools that we're building in order to analyze tractometry data. So this is work primarily led by Adam Ritchie-Halford. There's a preprint that I linked to down here that you can read that discusses some of these methods. So one of the main challenges in doing machine learning in these complicated data sets is that there's a fundamental trade-off between accuracy and interpretability. So if you look at the different algorithms that we can use, there are methods such as neural networks, trees and random forests, or support vector machines even, that have relatively high accuracy levels, but their interpretability is actually pretty low. On the other hand, we have linear models that are fairly interpretable, but usually in large and complex and high dimensional data sets, their accuracy is not as high. So one approach to improving on that is to take the linear models and apply regularized linear models such as lasso or ridge regression, and that makes these models slightly more accurate. It allows us to regularize the fits in a way that makes the models less prone to overfitting. But we really would like to go into this quadrant where we have high accuracy and high interpretability. And in order to do that, we use what are called group regularized models. Group regularized models, what we do is we treat the data as coming from several different groups. And tractometry data obviously lends itself to this kind of division because different parts of the data do come from different anatomical subdivisions of the brain. So let's think about this for a second. What I'm presenting here is a linear model. The Y are the outcomes. This can be something like whether the person is a patient or a control, or it can be a continuous variable, for example, the age of the individual. The X, every row here is a single individual, and X are the track profiles from different tracks. So here, these first few features are the track profiles, say the FA track profile from the corticospinal tract, and then the green would be the track profile from the cingulum bundle, and then this blue might be from the arcuate fasciculus and so on. And when we try to solve this as a linear model, what we're trying to do is solve for beta, the coefficients on each one of these track profiles, each one of the nodes in every one of the track profiles. How should that be summed together in order to give us a prediction, for example, whether this person is a patient or a control in a logistic regression setting, or the age of the person in a regular continuous regression setting. And what the group lasso or the group regularized regression allows us to do is to treat each one of these groups separately, one of these groups of features as coming from a separate group, and then regularize them separately. We use a method called sparse group lasso, which is a method that Noah Simon, our collaborator in the Department of Biostatistics, developed. And what that does is it balances between the regularization of the level of the groups and the overall regularization across groups. And this works really well. For example, here are the results from that ALS data set that I showed you before. The model predicts quite accurately who has ALS and who is a control. And very nicely, the beta coefficients, the weights in the logistic regression here are mostly on the corticospinal tract, which is where we know that there are the main differences between these two groups. Another topic that we're really interested in studying using these methods is development. Here's a complicated figure from a paper from Catherine Labelle in 2012. And what you'll see is that the white matter really changes in the age range that they studied here, which is sort of childhood to adolescence. But it's really hard to draw any, to extract insight from this. What we'd like to do in our modeling is to create models of what we call brain age. The idea behind models of brain age is that every individual has a chronological age, and for every individual, we will generate using the sparse group lasso a predicted age. That's really useful because if the model is very, very accurate, then now we can look at outliers. For example, we can look at this person for whom the chronological age is high, but the predicted age is rather low, and we can ask, why did this person's brain, what in this person's brain made that shift in that direction? Or we can ask also, let's say this is a person whose brain looks older than their chronological age. We can ask, what are the features of this brain that made that shift over to the right like that? So first we need to generate accurate baseline models, and that's what we've done using the sparse group lasso. We did this in 3 different data sets. One data set is a data set we'll call Western Havens. This is a data set that Jason collected a few years ago and published in a paper in 2014. Another data set is the Healthy Brain Network data set. Here we have about 1,000 individuals from the Healthy Brain Network. And the CAMCAN data set that I mentioned before that has this lifespan data set. You can see that the age ranges are quite different between these data sets. Nevertheless, in all 3 data sets, the models are rather accurate. You can see that the R squared for the cross-validated R squared for goodness of fit in these 3 data sets is quite high. So the models are really accurate. Okay, just like the other components of this talk, the software is available. Here, this software AFQ Insight that takes the outputs of PyFQ and fits these kinds of models is available at this website. And as part of our work on this, we separated out the sparse group lasso. We created a Python implementation of the sparse group lasso that people in other fields can also use on not only people who are doing tractometry. And we split that out as a project that we call Grouper. It's got scikit-learn compatible estimators for estimating the sparse group lasso. And we recently published that in a paper in the Journal of Open Source Software as well. So you can read about that. One final thing is, I mentioned that these data sets are very, very large. And the question is, how do we run this at the scale of a data set with 1,000 individuals, for example, which we did in the Healthy Brain Network? And the answer to that is that we use cloud computing to do that. Cloud computing provides a strong basis for scaling up. It's very scalable. You can get as many compute cores as you need. It's elastic. Once you don't need those machines anymore, you can shut them off and then you don't pay for them anymore. It's very, very reliable. And this makes the work reproducible because anyone with access to cloud computing, and that's anyone who has a credit card, can run the exact same scripts that we ran to get the results that we got. So it's highly reproducible. And this is the result here as a result of a benchmark study that we did in 2017 that just showed how you can scale using a variety of different big data frameworks. You can scale DIPY-based pipelines up to, and you get an increase speed up in performance as you increase the number of nodes in the cluster. That's kind of obvious. So as you saw there are many frameworks for big data analysis, but as we learned when we did this benchmark, you often need to do extensive rewrites of the code that you've already written, or you need to do substantial system administration to set up these systems and run your code on them. Instead, what we like to do is we'd like to do a minimal rewrite and minimal system administration. So as part of our work on DIPY, actually, we developed the software called CloudNot that runs your existing Python code in AWS batch. So this runs in the Amazon Web Services. The software is here, nrdg.github.io/CloudNot. And what it does is it scales already existing Python code to the massive resources of Amazon Web Services Cloud. One example is in this repository right here, where all of the results that I showed you before from John's work is available using Jupyter notebooks that take data, these very large data sets, and scales the PyFQ software using AWS Batch run through CloudNot. So that's an example of how to do that. Okay, finally, I'd like to thank all the various sources of funding to this work, and I'd like to thank you for your attention.